Good evening, everyone. I'm Bilal Shohaiber, team leader. I'm here with my colleagues Mithil and Vijay. We've developed an interactive earthquake data visualization tool using Streamlit and SQLite that transforms complex seismic data into accessible educational visualizations. This project addresses the critical need for earthquake data accessibility, serving students, researchers, and general public with real-time seismic information from the USGS API. Let's explore how we built this project. Next slide, please. This project integrates three core components. The first component is the user interface. We built it using Streamlit. It provides an intuitive web interface for users to filter earthquake by parameters such as data ranges and magnitude thresholds. Second component is the backend logic. We used Python scripts for it. It manages sophisticated API communications with the USGS earthquake surface. It handles complex GeoJSON data parsing and information into structured formats. It implements comprehensive logging for user queries and system events. It also prepares process data for dynamic display on the front end through optimized Panda data frames. The third component is the USGS API. It supplies alternative real-time earthquake data in structured GeoJSON format, which is queried dynamically based on the user's selected filters. Next slide, please. Our project hierarchy follows a robust three-tier architecture. The first tier is the user interface. It's built entirely with Streamlit framework. This tier handles users' input validation. It handles also real-time visualization updates and informative and interactive map rendering through seamless integration with volume mapping libraries. The middle tier, as you can see, is the backend logic, which contains our core Python applications modules, including the USGS API, database.py, and DB logger, which will be explained later on by my colleague. The bottom tier is the data source. It combines external USGS API integration for real-time earthquake data acquisition with our local SQLite database storage for data persistence and online analytical capabilities. Next slide, please. Our data module forms the foundation of our visualization system. By implementing sophisticated data management strategies designed specially for education and research applications requiring both accuracy and accessibility. The module handles comprehensive earthquake data, lifecycle management from initial API acquisition through final stages and retrieval operations. Our dual database architecture utilizes sophisticated SQLite database optimized for different data access patterns. This primary system processes real-time earthquake feeds from the USGS API while maintaining detailed historical records for long-term studies and trend analysis capabilities. Next slide, please. Our project demonstrates advanced Python engineering capabilities. It also demonstrates transforming raw seismic information into meaningful insights through the sophisticated processing and optimization techniques. There are two techniques that we are doing here. The first one is the live data fetching and API integration. And here we are retrieving real-time earthquake data from the USGS API using dynamically constructed URLs based on the user's input, such as the dates and the magnitude. The second technique here is the data processing and transformation. It processes complex GeoJSON responses and converts them into structured pandas data forms for sufficient and efficient filtering, aggregation, and visualization operations. The next slides will be explained by my colleagues.
Hi everyone. So now we'll be discussing about the different data cleaning and validation techniques we've used in our project. so we have implemented it in two ways. First, the comprehensive validation procedures. What this does is it removes incomplete or malformed records through a multi-stage validation process. And what this does is it ensures only valid entries with complete location or magnitude, and also that have a proper timestamp flow through the system. And we also have geographic validation, which verifies coordinate boundaries are within valid Earth ranges. And then we also have database communication and storage. What this does, it stores clean, validated data and optimized SQLite databases using parameterized queries. What this does is it prevents SQL injection attacks while ensuring optimal query performance. The earthquakes.db maintains comprehensive event data with strategic index for rapid retrieval, while the other DB, that's the query logs DB, records detailed user interactions for the system analytics, usage optimization, and research reproducibility. Due to this validation framework, we achieve a 95% data accuracy while processing even thousands and hundreds and thousands of earthquake records daily. Next slide, please. In the next slide, we are going to discuss the various local storage and modularity implementations of our project. So the first one is the SQLite storage implementation. This saves comprehensive earthquake data in a local earthquakes.db file, enabling complete offline access and data reuse without requiring much external server infrastructure or internet connectivity. This we did this because to enable to be beneficial for educational environments where internet access may be very little or unreliable. And we also other thing we implemented is the modularity. We have a reusable modular design we implemented primarily in database.py with clean and well-defined interfaces, enabling easy system updates, future scalability option, and seamless integration with additional seismic data sources or analytical tools. The modular structure supports independent components testing, simplified maintenance procedures, and straightforward enhancement implementation without affecting the other system components when they are down. What this does is it enables zero configuration deployment requiring no database server setup or administration, and it also provides full asset compliance, ensuring data integrity during concurrent operations and data issues. Moving on to the next slide. Uh, Now we are going to discuss the two modules of our project. In this slide, we are going to discuss the front end module. So what we did is we built this with the Streamlit framework, which is developed entirely using Streamlit framework, completely eliminating the need for separate HTML, CSS, or JavaScript component while still providing professional web application functionality. This approach, what it does is it enables rapid development cycles and simplified maintenance procedures. And then we have the user input components. What this does is it enables users to set their custom filters through intuitive interactive sliders for magnitude, threshold, comprehensive date pickers for temporal range specification, and etc. The interface provides immediate visual feedback for all user interactions and implements client-side validation. And then we have the live data display capabilities. What this does, it automatically updates charts, tables, or interactive maps in real time based on user selected parameters with no page reload required, creating a smooth, responsive user design. All these advanced features include comprehensive CSV data export functionality also additionally for external analysis, and also fully responsive design supporting both desktop and mobile access. Next slide, please. Yeah, in this slide, we're going to discuss the backend part of our project. So what we did is we implemented it in three different ways. The first is the unified Python implementation. The entire backend is implemented in Python, managing complex API operations, advanced data processing and transformation procedures. And we also have comprehensive database interactions through specialized purpose-built modules. This unified approach, what it does is it ensures consistent error handling across all system components, and it also enables seamless integration between different functional areas. And then we move to the API part of our project. Uh, we have an advanced API integration which retrieves earthquake data from USGS API using dynamically constructed URLs based on user-specified filters, including date ranges, magnitude thresholds, like we discussed before. The system implements intelligent retry logic, which also is backed by the exponential backoff algorithms. This handles various API response formats and edge cases. And then we move on to the data processing part of our module. Uh, We have a sophisticated data processing which parses complex nested GeoJSON responses and transforms them into well-structured Panda data frames. The processing pipeline handles nested JSON properties extraction, validates data integrity at multiple stages, normalizes coordinate systems for global compatibility, and optimizes memory usage patterns for processing large data sets. Uh, Now my colleague will continue to the next part. Thank you.
Hello. So in this slide, we are going to talk about the DBMS module we've been using in our project. So our DBMS module it basically consists of persistent storage, comprehensive logging, and secure database operations using SQLite. So the database management system provides reliable, efficient storage solutions for both real-time earthquake data and comprehensive user interaction logs. Our implementation demonstrates advanced SQLite optimization techniques, including strategic indexing, query optimization, transaction management, while also maintaining the essential simplicity required. So the key design principles include full asset compliance for guaranteed data integrity during concurrent operations, strategic indexing, implementation for optimal query performance, and exclusive use of parameterized queries for robust security against injection attacks. So the DBMS module we've been using is specifically tailored for lightweight deployment while maintaining future scalability capabilities. So in the next slide, we are going to look at why we've been using SQLite. So in this slide, we have been using SQLite for two different reasons, and they are due to file-based DBMS architecture, as it requires no external server infrastructure or complex configuration procedures, making it ideally suited for single-user Streamlit applications and educational deployment scenarios. While the seamless Python integration works natively with Python through the built-in SQLite 3 module, enabling highly efficient database operations without requiring additional dependencies or external libraries. And moving on to the next slide, we have been where we can see the database and error management techniques we have been using. Our database and error management technique system ensures reliable yet consistent operations through comprehensive error handling strategies and robust data operation procedures. In the comprehensive database operations section, it utilizes SQLite 3 to manage earthquake databases for comprehensive earthquake event data and query logs for detailed user activity, tracking all the system analytics, as this helps all operations to be employed in a transaction-based processing to ensure complete data integrity and implement strategic indexing for optimal query performance across various access patterns. And the robust error handling techniques leverages sophisticated try-except block structures combined with Python's comprehensive logging module to handle API communications, errors, invalid user inputs, unexpected system failures, and database-related issues gracefully. While the error management comprehensively covers multiple failure scenarios, including a network timeouts during API communication, database log conditions during concurrent operations, disk space limitations, all the error conditions are systematically logged with detailed contextual information for effective debugging system, monitoring, and continuous improvement process. In the next slide, we are going to talk about the logging and security features we have been providing. In the comprehensive query logging, the specialized database logger.py module maintains detailed logs of all user queries, including precise timestamps, applied filters, result counts, and interaction patterns for complete system traceability and research reproducibility. And the next technique, the advanced security implementation, provides all SQL databases with queries exclusively to use them for parameterized statements to completely eliminate SQL injection vulnerabilities while maintaining optimal query performance. And we have also been looking out for the future by providing future scalability architecture. In this architecture, the modular design facilitates with easy migration to cloud-based DBMS solution as usage requirement grows, supporting future enterprise deployments while maintaining current educational accessibility and simplicity. While the logging framework provides detailed system monitoring and performance analytics while carefully protecting user privacy through anonymous interaction tracking methodologies, ensuring all sorts of compliance with education privacy requirements and research ethics standards. Uh, well, thank you so much. Thank you so much for giving us this opportunity to present our interactive earthquake data visualization project presentation. And we're open to all sorts of questions. And hope you guys enjoyed it. Thank you. Thank you from my team.